what we're doing in here, not as a substitute for coming to class, which you're immediately thinking of, but just as another thing you can look at if you happen to miss class because you're sick or you overslept, which doesn't matter what time of day the class is, people will say they've overslept, or if you're out of town or whatever, sick. If any of those things happen, we're going to try to capture an archive of what we talk about in lecture and discussion. So it's an experiment. If you don't see me start a recording at the beginning of any section of lecture, please start mumbling or do something that indicates that I have forgotten to do this. But I don't guarantee a perfect record, but it will try to do that. So what is this class? This is, for those of you who are wondering, this is CS 537. Yeah. Yeah, voice also. Yeah, it's voice and screen and your questions forever on YouTube for people to comment on years from now. They'll say, what a terrible question at minute 16. Watch it. So just think about that when you're about to ask a question. I'll actually turn off YouTube comments, so you won't have to see that, so don't worry. Yeah. Is anyone watching this in 2033? No. So, okay, so this is CS 537, and this is generally called the kind of introduction or whatever operating systems course. And we're going to do a few things today. First, we're going to understand that we are all in this together. It's a brutally scheduled, it's just 3 hours, right? 3 hours together, so we'll try to break that time up a little bit. Someone already asked me, will there be any breaks? The answer, of course, is yes, there will be breaks. We'll have points to pause, and you can actually then get up, stretch, run home, whatever you need to do. There will be time for that, and we'll try to break up the time so we can, of course, the problem is we have to use all our time very preciously. We have exactly 14 3-hour lectures in which you are supposed to learn everything you need to know about introduction to operating systems. So we will use that time judiciously, and therefore that means you have to be able to pay attention as well at the end as you are paying attention right now. Now, if you're not paying attention right now, well, I don't know what to do about that, sorry. But this is usually the time where people pay attention. So let's get going a little bit. Conceptually, I think of each half of class as a kind of a full lecture. So we're really doing two lectures today. And what those 2 lectures are part 1 is really just an intro lecture where we talk about the class and we talk about what we're going to learn. And then, unlike other classes where you have a little bit of a light intro, we have to do like a real lecture, right? That's the second lecture is some real information, and we're going to start getting into the notion of what is a process, which is an important OS concept, and the beginnings of understanding what CPU virtualization is. So that'll be part 2 of today, and we'll talk more about lots of things throughout both the intro and the second part of class. And of course, like I said, we'll take breaks throughout there so that we can wake up again, stretch our legs, etc. Talk to our friends whom we haven't seen since last fall, because of course, it's nice to talk to people too. Okay, so let's answer a few questions first. Let's answer this question: why study operating systems? That seems like a good question. I mean, of course, some of you are answering that question with, I had to take something and you're requiring either this or that other class, and this one fit my schedule. So that's okay. That's a good reason, because we think it's important for you to take it. But I don't know, why do people want to study operating systems? Yeah. Oh yeah, sure. Learn something about security. Operating system it's not a system security course, but the fundamental tenets of operating systems relate to creating a protected environment on which to run programs. We've seen this in the news lately, actually, if you've been following around with Spectre and Meltdown and these huge CPU bugs, which are actually causing major problems in the world right now. How many people have followed along with that? Some of you? Yeah, so pretty fascinating stuff. Of course, to understand those bugs, those processor bugs in detail, you have to understand how processors work, modern processors. You have to understand how operating systems work. You have to understand some security concepts. What we'll try to do is get the OS part in this class for sure, and maybe we'll have enough time at the end to talk a little bit about what other stuff you need to know to really understand that. Maybe we'll do that at the end of class. That'd be kind of fun to go over at least one of those bugs, because it certainly relates to some OS things that we'll talk about in class. So very timely and certainly good to learn about security because the world is forever going to be insecure. So that's a good reason. Why else? Yeah.
Application portability.
Okay, learning something about applications and generally like issues about portability. Sure. Understanding what that even means and why do we an operating system creates a programming environment for applications, so we should understand something about that. What else? Yeah.
Why Windows keeps crashing.
Why Windows keeps crashing. Okay, sure. That's a good reason. Let's call that reliability. Very much an issue in operating system is how to keep running despite the fact that users do terrible things. This was less of a concern in early operating systems, but the lesson was learned and relearned. Like when you had a DOS was a very simple operating system, but you wouldn't even really call it an operating system by modern standards because it had essentially no protection. It was easy for any user to crash a system. On modern operating systems and even Windows-based operating systems, it's much harder because we have a lot of hardware and software mechanism, and we're going to, of course, learn about all those mechanisms. So those are good reasons. Anything else anyone wants to add? Yeah?
File and program management.
Okay, sure. Talking about files and program management, sure. Certainly one thing we'll be talking about at that third part of class, and we'll talk about how class is divided in a second. We'll be talking all about file systems and how we store data persistently. Of course, computers, we have to eventually figure out how to keep data around if we care about it. And so we need to understand what that means from the design of the systems that we care about. So those are all good reasons, and I think you could all go on and give many more. I'll give a few reasons myself. So these are the right answers for the exam. If you're paying attention, no, that's not true. These are all actually very good answers. And really, one thing that I would think about is one thing that I think is important that you get out of OS class is you really get a sense of how computers work. I mean, it sounds pretty simple, but a modern computer in how we use it is defined by the operating system. So everything you see and you kind of interact with and all the very fundamental abstractions that we're going to talk about, like what is a process, what is an address space, which you've gotten a preview of in CS354, we're going to talk about a little bit more deeply, and we're going to understand those abstractions in a really deep way. And that's just, you need to do that to understand how systems work. It's just a good thing to know. I think another reason is just fundamentally it's interesting. Now, I'm biased in this regard, and some students tell me I may be wrong about this. You'll have to judge for yourself if you find the topic interesting. There's a bunch of conceptual things that I think are pretty cool that have been developed over the years in order to understand how to build modern, reliable, secure computer systems. And those are all, human creations. It's amazing. These people sat down and thought of these things, basic things that we take for granted today. So we're going to learn about those things, and they really are wonderful. And then here's the kind of the good news, bad news. We're going to learn about a little bit about how computers work, but there's so much more. This is the reality. No matter, there's an old saying, it goes back to Goethe, who said, the more you know, the less you know. And that's going to be absolutely the case with operating systems or computer systems in general. When you learn about some facet, I finally understand a little bit about how virtual memory works, or how a file system works, or how concurrency works on a modern system, you realize that you're just beginning to scratch the surface. And if you're going to go work in the computer industry, which a number of you probably will, the reality is the modern data center is so complicated. If you're talking about like an infrastructure at a major company like Google or Microsoft or Amazon, there are just so many different pieces to understanding how all those systems work together that we're just going to give you the first foothold from which to kind of get a vantage point on how you might begin to understand such a world when you're thrust into it later in your life. So this is a good class to take in order to kind of bootstrap yourself in that direction. Okay, so that's why. Hopefully those things sound good, or one of them sounds good. I've learned a long time ago from an old mentor of mine that when you're motivating people, you just give a lot of motivation for things, and then they only need to find one reason. So if you say, hey, one of those sounded good to me, but yeah, I guess that other thing is, I had to take it. I have to write that down. I had to take it. That's why it's such an interesting thing. So what we're going to talk about now, we'll do a little bit of background, and then we'll start to talk about this most fundamental question, which is, kind of what is the operating system and what does it do for us. So let's do that in order. Let's talk about background. And the particular background is kind of stuff that I will essentially assume you already know or already remember some of so that you can go relearn and remember enough of in order to be successful in this class. There's really two prerequisites for this class. One is CS, well, what is it? It used to be 367, now it's probably 400. Does 400 exist yet? I don't even follow these things. Yes, it does, right? Is anyone taking CS 400? Okay, not so much. Okay, so in any case, who's taking 367? Yes, okay, good. So this means you have some ability to program. Computer science, of course, isn't just programming, but to be a good computer scientist, you have to be good at programming, right? It's a skill that's part of what we do. It's a basic skill. And the more you do of it, there's no way around this. The more you do, the better you get. So finding excuses outside of the things we force you to do is always a good idea because that's really how you get good at things. So of course, we're going to assume that you have some basic programming. Some of that's in Java, a little bit you've done in C, I presume, and we'll talk more about C quite a bit because that's the whole class will be you writing C programs of some various flavors. The other aspect of this class that we assume is that you have had CS 354, which is basically an introduction to computer systems. There, and a little bit of, you get a little bit of OS in there too. There we think about, how a computer works at a very simple level. The amazing thing about computers, why did I go into computer science? Well, at some point, what a lot of people who are technical or technically minded get interested in math and physics and chemistry and the basic sciences. And at some point, I realized to go into those fields and be successful, you really have to know a lot of stuff. Physics is very complicated, chemistry is very complicated, biology is very complicated. And then when I started to learn about computers, I'm like, computers are really simple and we created them, so how complicated can they really be? Nature may never give us certain answers, but with a computer, we should be able to figure it out because we created it as human beings. So that excited me. I felt like that was something I could wrap my head around. And if you think about a computer, why it's so simple is because we have just a few basic components. We have one or more CPUs, processors. I'll use those terms interchangeably. The processor has instructions and data in a memory, right? So that's where we operate on. And without thinking about other parts of the computer system, we think about just a very simple thing that the processor does amazingly billions of times every second. I mean, it's still hard to get your head around that, right? No matter how many times you say that, it's impossible for us to imagine how much a computer does in a second. And what does it do? What does a computer do to execute a program? Is it does something you probably learned about: fetch, decode, and execute. So every time we want to deal with an instruction, every time we want to do something, what the CPU does is it goes and gets an instruction from memory, brings it back over here into some sort of closer by memory, then figures out what the instruction is, and then actually does the instruction. And the instructions are these amazingly simple things, right? Like adding two numbers together, or comparing some numbers, or jumping to some other piece of code based on some result. It's all so simple all the way down at the bottom. And it's amazing how much complexity we've built upon this very base simplicity, right? It's really stunning to me how much we could do with just these little automatons that really, per instruction, don't do anything. It's the fact that we can do billions of these things that makes them interesting. So this is the fetch, decode, execute loop. You probably learned about that in 354. At least it should seem familiar or understandable. But that's not the only part of a computer system, just CPU and memory. And let me just make sure we understand. There are two types of things in memory. There are instructions and there's data, right? That relates to this basic thing we call the von Neumann model of computing, where everything is in some sort of store, and that including the instructions themselves. So what other parts of the computer system should we care about other than CPU and memory? Yeah. Yeah, some sort of interface to the humans. I like how you said that. It's like these humans that we hear about. Yeah, there's some interface to the humans. Like, for example, there might be a display That might be something that we care about. We might care about, for example, some other kind of thing like a keyboard. Here's my artist friend. You'll learn throughout the class that I'm not a very good artist, but I do draw a lot of boxes. That's most of my artistry is in the form of boxes, so you'll have to forgive me. We'll even connect a mouse to this, which will make an oval. So that'll be a new thing for me. That's a mouse. Yeah, so we need some interface with the humans. What else? What's another important part? Yeah. Yeah, sure. Some sort of connection to the outer world, a network. One last piece that we're going to talk about a lot. Yeah, some sort of, I've run out of room over here. Oh, let me check out the iPad cut and paste. Let's check this out. I'm wildly excited by this. That's pretty cool, right? And the third time I do it, you won't find it cool anymore. But that's okay. So anyway, let's just make this a little bit longer. And then over here, we'll add some sort of a disk or a hard drive. It used to be that these were always just rotating magnetic media. Increasingly, it's being replaced by what we call solid-state storage. We'll talk about both those things. They both turn out to be important today, and maybe for the next 5, 10 years, eventually probably hard drives will be replaced with just all solid-state, but today they still matter. So these are all important pieces of a computer system, and we're going to, of course, talk about all of them. So I'm going to assume that you know these things, and I assume you have a basic idea of at the low level, at the instruction by instruction level, and we probably learned a little, x86, right, in 354. Does that sound familiar? Yeah. So that we're going to assume that you know what that sort of machine instruction by instruction is. Yeah.
So are we still going to work with x86, or are we going to work with AMD's implementation of 64-bit?
Yeah. So we'll talk about all of that in a moment. Yeah. So the question is about, what exactly are we going to do? How are we going to do projects? What's the, assembly language? What's the high-level language we're going to do? I'll talk about all those things momentarily. So you'll be left in suspense until that moment, just wondering. Okay. So that's how a computer works in a nutshell, and really, it's amazing. If you understand that, you should be able to understand everything that goes on in a computer system. Now, an important piece is, we understand things at a low level, but we have to also turn that understanding into slightly higher level understanding. So, for example, at the C programming language level, that's more or less what we're going to be doing. So I'll preview that right now. We're going to be doing C programming. I mentioned it earlier too. And C is a pretty low-level language. The nice thing about C is the more you understand about C, the more you can kind of understand, you can kind of look at the C code and essentially know what instructions are executing more or less. Now, compilers are very smart and do lots of crazy transformations, but you should have a basic idea when you write C code what's going on the computer, or what you intend to go on the computer. So, for example, when we see, I'll assume that you know things like, I assume that you know C to some extent. Somewhat. You don't have to be an expert, but you've written some programs in C, hopefully, because we're not going to have a lot of time we'll do a little review, but we won't have a ton of time to do that. You should know things, for example, like let's say I write a function like this. I call it increment, and I pass it an integer, and I say x equals, now who would write a function like this? Nobody. But let's say you did. Let's say I write a function like this, and then down here, some other part of the code, I have a variable integer y. Let's say I set it equal to 10, and then I say, you know what, I want to increment y, and I forgot about the old plus operator, so I called inc instead, and I called inc on y, and then I print it out down here, and what value do I get? 10, all right, excited crowd yelling 10 at me. Yes, and why is that? Why is it unchanged? Oh, sorry. Just somebody raise their hand. Otherwise, you'll all say the exact same answer at the same time. Yeah.
Why isn't it a global variable?
That's definitely true. Why isn't? But in general, what's the problem with writing a routine even like this? What's the point of writing this routine? Yeah. Yeah. In fact, what's getting changed when I call this routine is what C does is when I call a function, I have this thing called the stack. And what I do is I create a stack frame, right? I create a stack frame, and all my local variables, including parameters I pass to the function, I create up here in memory, and they're initialized essentially with a copy of the value of y. So essentially, I create y maybe is down here, and the value is 10. When I call into inc, I create a space for x on the stack. Then is that big enough, by the way? No, that's bigger. And then I go ahead and initialize this to 10. Sorry if that's too small. Then I'll draw bigger diagrams from here on out, or so I promise. Then, of course, when this code executes, it does do something. It increments this to 11 here, but you can see that the value y down here is unchanged. So I'm going to assume that you're kind of know about things like this, like that when we have a running C program, that we have a stack. We have, of course, our code that we're executing. And, of course, there's a third part of memory, which is pretty important. What's that?
Oh, the heap.
The heap, right, the heap, right? What's in the heap? It's whenever we need dynamically allocated structures that don't naturally kind of come from our stack allocations that we get when we allocate variables on the stack when we're calling in and out of various functions. So I'm going to assume things like you should know that, a C program you think of as code and a heap and a stack. And, there's some other stuff in there too, but this kind of basic terminology around how a C program runs should be something that's familiar to you. If it's not, well, you have, I guess, a couple choices. One is to say, oh, I'm going to go learn that stuff and take this class later, or I'm going to really learn it now because the projects are going to start and make sure I get up and running effectively soon. Okay, so any questions about that? Does that make sense? Sound familiar? Okay. Sound like that's not a question that's going to give an answer, so I'll assume the answer is maybe. Okay, so now what I'm going to do is that's kind of the background for the course. Any other concerns or worries about, am I prepared to take this course, that you're willing to ask in public? Otherwise, if you have a concern like, hey, I'm not sure I'm quite ready for this course, please feel free to see me at one of the breaks or after class. Yeah? Am I bringing back the shirts? Oh, yeah. So we've done in the past some contests for the projects. I think you're getting ahead of yourself here, already anticipating a contest and perhaps winning the contest. But I like your enthusiasm. Yeah, so we've done contests for some of the projects before where we basically have some sort of metric, like who wrote the fastest program that could do X, or maybe who did X in the fewest lines of code and still passed all the tests. I will talk about that. We will do that probably a couple times in the semester. And then the winner gets, of course, eternal glory, if nothing else. But beyond that, it's a pretty, you walk around campus, people shake your hands, it's pretty exciting. But other than that, you get a t-shirt, kind of a crummy t-shirt. So that's also something to look forward to. So yeah, we'll do that. We'll do that a couple times as is appropriate. Okay, and those are kind of fun because basically that turns a project which you only spent 10 hours on into a project that you spent 40 hours on and still didn't get a lousy t-shirt. So that's a nice property. Okay, so let's transition into another piece here, and then we might even get to, I'm trying to figure out how often to take breaks. I'll probably try to do it every half an hour, 45 minutes, or whenever I see everybody's eyes start looking over there, as I get a majority of eyes looking there instead of at myself, what we'll do is we'll take a break. So let's get through one more thing. I want to get through a little demo of a little bit getting at this real question here, which is OS, kind of what is it? What's it doing for me? And what kind of things are we going to learn about? And we'll do that with our old friend, the terminal. Okay, so now we have to make this legible for the people who sit in the back and don't want to be anywhere near me, which I don't take too personally. Okay. So let's look at a program. Yes, I am an Emacs user. There's a historical reason for that. Is one of the first jobs I had as an undergrad was in an AI lab. And in an AI lab, you use Emacs, or at least you used to. I don't know what they do anymore now that AI actually works. The world has changed so much that I can't really comment on it. But that's something we can talk about later. Okay, so how about for 30 seconds you stare at this very non-complicated program, and in your mind or with your neighbor, figure out what this program is doing. It's not a complicated program. Can people in the back read this, by the way? Can you read this? Does anyone not read this? Can I make it bigger? Should I make it bigger? Okay. I'll make it this is as big as I'm going to be able to make it, really. Oh, and sometimes they say I should switch the colors. I forget what. No, I'm trying to remember what the color theme is. Let's see what happens. Is that better or worse? Worse. Better? No. They're like, he's an idiot. Oh, he's kidding. Which? Both. He's an idiot and he's kidding. Says this guy, whose face I'm going to remember for sure. So let's try classic. Worse. Christ. I'm going to give it dark blue. Oh, these are terrible. In the meanwhile, you're reading the code instead of paying attention to my idiocy here. I have an idea. Yeah, perfect. Okay, we'll go with this until I find something better, which I will experiment with offline. Okay, so what does this program do? It just prints. Yeah, it prints whatever you passed in over and over again. You don't know what one piece of code does. Spin. This just does nothing for a second. Okay, so every second this just prints something out that you passed in on the command line. You remember our old friend argv, and you should understand things like this. Questions about the code? Make sense? Okay. Now, this isn't too exciting. We can, of course, compile this with our old friend, the compiler. And I always recommend, in fact, we will force you to turn on all warnings. And, in fact, flunk, if you have a warning, turn it into an error so that you can't compile the program if you're generating warnings. So you have to have a clean compile to pass a single test in this class and pass the class. There's no having my code and turning it in and having a bunch of warnings in it because that's just sloppy. So it would be our slight discouragement to you to being sloppy like that. So let's see, I'm not sloppy, so that's good. And let's go ahead and run this program. This isn't too exciting. It's going to do exactly what you thought, which is print hello every second. But what's kind of cool that the OS lets me do, and this is, if you think about 354, I kind of think of 354 as really understanding in detail what one program is doing when it's running. What the OS class is really supposed to do is let you understand how the OS creates a beautiful abstraction of I don't have just one CPU, I have as many CPUs as I need. And how I do that is I can run this program, many of these instances of this program. Let's pass it some different arguments, and let's go ahead and let's see what this does. So I'm going to run 3 at a time, a couple of kind of shell things here. I'm passing some different arguments, a space in front of a 2. I put some quotes around that, and 2 spaces in front of a 3. And then I'm using this ampersand after each command so that when I run the first one, if I don't have an ampersand, I'll just wait till that program's done before launching the second one. I want to instead put all these jobs in what's called the background in Unix and run all of them at the same time. And you can see what happens, not surprisingly, is that all of them are running. And of course, I could do that for 1,000 different programs, and that would essentially work because let me kill these now. There, we're done. And why I can do that is because the OS provides this amazing abstraction of I have as many virtual CPUs as I want. It's called virtualization. We're going to talk a great deal, or a little bit at least enough, to learn what it means to really talk about CPU virtualization and how the OS creates this beautiful illusion of that I have many, many CPUs. And why do I do that? Why do I care about that? I mean, I have lots. What's nice, even on my, on my laptop, I have 4 CPUs or 4 cores, and many have 8 or soon 12 or 16. Why do I want to be able to run as many programs as I want at the same time? Why do I care about that? Yeah. Efficiency, yeah, that's a great example of a good answer to this, because one thing that when I'm running multiple things at once, it actually lets me better utilize my hardware. Now that was a bigger deal like in the era of the mainframe, and we'll talk a little bit about this throughout class when we hear the history of multi-programming. in the early days, a university like this might have one computer for the whole university, which means, of course, that you really, and it was millions of dollars, which means you wanted to utilize every cycle as efficiently as you could. So when you're running one program and then it went to, say, do a disk I/O, or maybe back then even like a tape I/O, it would basically not be using the CPU and waiting for a very slow, say, disk drive. What multi-programming, what this kind of sharing of resources lets us do is when we're running one program and it gets stuck doing something slow, like waiting for a network message to come in or waiting for a disk I/O, we can then switch to something else. So efficiency is one reason. What's another reason? Why do we like to be able to have as many CPUs as I need? Yeah. Yeah, multitasking, right? It's actually just kind of like ease of use. I want to be able to do whatever I want. I want to have a browser up. I want to, have a music being played. I want to, of course, be writing my code for 537 and carefully debugging it. I want to be able to do lots of things at once, and I don't want to be limited by the physical hardware that I have. And so the abstraction of having many virtual CPUs is very much about ease of use. It allows us to just, whenever we want to run a program, we don't have to think, do I have a CPU ready for this or not? I just run a program. Okay, so that's virtualizing the CPU, and that'll be one thing that we talk about, of course, in some detail. Let's look at another program, mem.c, very great names. This is a little bit painful to read because I left a lot of comments in here. Okay. Anyway, what is this doing? So what this program does, it's not very complicated. It just basically takes some memory value and then just increments that location over and over again, okay, and then prints out the value, okay? And then what's kind of neat about it is when I run this a few times is, let's say this one will start at a value of 2,000. One thing you can see in this program, and then I'll go ahead and kill this program, is that when they print out the address that they're updating, each of them thinks they actually are updating the same address. But the OS has provided an illusion, and again, you may know this a little bit already, which is that each program has its own private memory. Just like each program thinks it has its own CPU, or maybe multiple CPUs in a multi-threaded program, the OS gives an illusion that there is a memory that you have, and it's private to your running program. You don't have to worry about is somebody else using memory. It's a beautiful abstraction. It makes it easy to program. It also gets at security because it means that when I'm writing to my memory, I don't want to be able to write to your memory. You don't want to be, I don't want you to write to my memory. I don't want to be able to write to your memory because those are separate programs. Those are boundaries we're creating. And we certainly don't want to be able to write to the operating system's memory. So we're going to create an illusion of our own private memory, and that's called virtual memory. And it's a very fundamental abstraction also provided by the operating system. Let's look at two more programs. They're even more exciting than these two. Here's one. Okay, why don't you stare at this piece of code and figure out what it does? Even if you don't know the system calls exactly open, write, fsync, and close, but you can probably guess what those do. So why don't you take a peek at those and then spend 30, why don't you just talk about it for 30 seconds with your neighbors. And if you don't know who's next to you, introduce yourself, say hello, meet a new friend. Who knows? They may be someone you know for the rest of your life. They may be someone that you never see again. Both of those are possible. It could be your future, who knows, future best friend, spouse, sitting right next to you. Could be. I'll do that. Okay, good enough. By the way, that is a highly satisfying crowd murmur, which the people watching at home will really appreciate. So it's very pleasing to hear. It sounds like everybody's energetically working on something. So, and we did not stage that, future listeners. So anyway, what does this program do? What it does is it opens a file called /temp/file. It creates it. If it doesn't exist, that's what that little create flag does. And open. It says it's write only, so you can only write to it. You can't read to it. And if it does exist, it truncates it, which means it makes it 0 sized if the file had existed already. And then it sets some permission bits. This is that last bit to open. That's over here. And you can read to learn more about something like open, you just read the open man page, which of course is very good bedtime reading. If you're, for example, wanting to go to sleep or something like that. But man pages are very useful, and we'll learn in this class how to read man pages, because you have to learn how to read documentation if you're going to be good at anything in computer science. Then we have a little buffer, and we just put a little message in there that says hello world. And then we simply do something very simple, which is we've opened this file, and now we write to it. So we're creating a file on, say, in a file system. We're just writing out these exact characters, hello world followed by a new line character. Then we, as we do in both of these cases after opening and writing, we assert. We use an assertion to check, hey, did the right thing happen? Like when I opened, did it actually return the file descriptor, or did it fail? And when I wrote, did it write the right number of bytes, the correct number of bytes, or did it fail? And it's good to know that. A good C programmer, this isn't the world of Java, where when things go wrong, exceptions fly, and then you have to put like a big try catch around everything. Here we have to just check return codes. It's our responsibility. In fact, Java was created by people who had a deep knowledge of C programming and its foibles, I guess. And so what they said is, let's make it so that people can't kind of just ignore return codes, because sometimes things do go wrong, though most of the time they don't. Then we print out how many bytes we wrote. We call fsync on the file descriptor. Does anybody know what that does? Yeah. Yeah, that's right. So both of you said it. That's kind of cool, because next we're going to be talking about concurrency. But that's exactly the right answer, which is when you do a write in a Unix file system, we'll learn about this, it actually just puts it in memory, and then much later, say 30 seconds later, it flushes it to the hard drive or the SSD. Now, why does it do that? Why doesn't it just write it to the disk or SSD? Yeah. It's a really slow operation, right? In fact, that's often the answer to questions in this class. Why don't we do it that way? Because it's really slow, or it's really like a bad way to do it. So really slow is exactly right. So what the OS does in this case is it buffers those writes, but if we really want to make sure it gets on the disk, we can use this interface, say, please force that to the disk, and then close the file. So let's go ahead and run this. Let's make sure this file isn't here already. So it doesn't exist, and then we do that, and then we do that, and we see that it worked. Now that's not too interesting. What earlier I did, though, is I looked at this, I created a trace. I was using a particular kernel tracing tool that shows you when you do this, run this little program, how many functions inside the kernel are called during the execution of this program. Now remember, the program was very simple. Open, write, fsync, close. And then this is what the kernel did for us in what we would call the file system. So all of that work, and we could go through and try to understand that. It'd be hard to understand, and I could show it to you in more detail later. The file system is another piece we're going to study. How do we do all the work that's needed in order to commit data to a disk or read data from a disk? It turns out there's a lot of detail to that, and we're going to learn about all the techniques that people use in modern file systems. We're going to learn about virtualization. We're going to learn about file systems. A fourth thing, and the last thing that we're going to learn about is concurrency. And let's look at a little program already that does a little bit of what we would call concurrent work. Now, I'm going to compress this a little tiny bit in an awkward way, like this. But how many people have written a program that had multiple threads inside of it? A few of you. Do you do that in a class or just for fun? Fun, all right, I like that answer. Tricked you into saying that. You said computer programming is fun, which is awesome. Okay, is there a class that teaches that at all? Not so far. Okay, cool. This class, great answer. So what we have here is a program, and I'm going to just try to describe it at a high level. Of course, we'll understand this in great detail later. But we're looking at pthread create over here. What that's doing, one thing we're going to notice about it, I'll just point it out on the screen here, is it's basically, it's kind of like creating a function call, executing a function call. And in fact, this pthread create, it's kind of like calling into worker right here and then running this piece of work. The thing that happens when you create threads is instead of executing one function and then executing the next function, what threads allow you to do is have those functions run at the same time inside of your same program. That's called a multi-threaded program or a concurrent program, or in some cases a parallel program. And it's useful in many, many different cases. It's useful in building web servers, and we'll talk about in servers in general. We'll talk about why that is. And it's useful in building like a parallel program when you have a lot of work to do and you can use more than one CPU. You can create a thread that works on each CPU and gets the work done faster. So we'll talk all about concurrency later. Now what we're going to try to do with our very brief introduction to concurrency is understand what this program is doing. So we have two threads here, okay? And they're both going to be running the same code, the worker, at the same time. And in fact, they're both updating the same counter repeatedly in a loop, okay? So does the code make sense? Like let's say I wanted to update this counter. One thread's updating the counter 10 times and the other thread's updating the counter 10 times. So when I print out the counter at the end, the value should be 1,000,000, 20, no other choices. Yeah, it should be 20, right? So if I ran worker twice and loops was 10, just like in a row, I'd like it to be increment 10 times and then say increment 10 times. Does that make sense? I want to make sure this example makes sense at least at a high level what it's trying to do. Any questions about it? I feel like I haven't quite explained it enough. Kind of make sense? Any questions? Let's just run it and see what happens. Threads v0, it says how many loops. So remember I said if I give it 10 as the number of times to go and increment that counter, we have two threads, so each of them should do it 10 times and we should get an answer of 20. Now, what turns out to be very tricky about concurrent programs is they throw off every expectation of simplicity you have with computer programs. And that's because when we run these long enough, we're going to get into a problem. And let's say I run it with 10,000. What would I expect the answer to be? 20,000, okay. Was 20,000, okay. So that seems to be working. Sometimes. Let's run 100,000. Now, that doesn't seem like something a computer does. Give different answers every time. And the reason is, it's a very deep fundamental reason about how you build concurrent programs, but when they access shared data, very funny things happen. In fact, to really understand this problem, which we will in the middle section of the class, you have to understand at an assembly level what's happening. In fact, if you think about updating a counter, what's a kind of common instruction sequence that would update a counter? Like what at the assembly level, what would happen to update a counter? What would you do what instructions would you execute? Like you have a counter in memory, how would you increment it? Yeah. Yeah, perfect. If you didn't hear that, normally in sequence to increment a value is you load something from memory into the processor, and then you increment it, and then you write it back to memory. The problem occurs, that works perfectly well when just one entity is updating the counter. When you have multiple entities updating the counter, they both read the same value, increment it to the one up, and then they both store one up instead of two up. We call that a race condition. We're going to talk about that in great detail and understand some of these fundamental problems of concurrent programming, which are common in operating systems and now common in multi-threaded programs as well. So very weird, interesting, kind of bizarro behavior from what we otherwise expect to be very deterministic machines. It seems like there's a non-deterministic behavior, and then we're going to learn, of course, how to fix that. And how we fix that in this case is something, and I will take a break after this fix, is we use something called a lock. A lock guarantees that at any point in your code, that only one thread will be doing the critical thing at a time. And by doing that, we can make sure that no sort of race occurs between threads. Here, we make each thread grabs a lock, increments a counter, and then lets go of the lock. And so we could see if we run threads v1, not that this proves anything, but you could imagine that it's going to work because otherwise I wouldn't be doing this demo, and actually most of this class would be a fraud. So, it is a lot slower. This is an excellent point. Sometimes there's a cost for correctness, and we'll talk all about that. And of course, we'll talk about how to even optimize a simple thing like this. Okay, so perfect stop point for a break. Break number one. We've seen a little bit about some of the things that the OS does. Then we'll talk about its roles a little more formally and then get into other material.